When we talk about the center of a distribution for a quantitative variable, there's two different things that we might be referring to. One of those is the mean. We use different notation for the mean depending on whether we are looking at data that represent a sample or a population. So if it is a sample, we use this x bar, which we pronounce x bar just because it's an x with a little bar over it, so of course. If we are working from a population, we use this Greek letter mu. Looks kind of like a U, but it has an extra little tail at the front. In both cases, the mean is calculated the same way, which is by adding up all of the values and dividing by the number of values in the list. In this formula, you'll notice a symbol that you may not be familiar with, which is this another Greek letter, but this one is capital sigma. We will also use lowercase sigma in this course for something else, so right now I want to emphasize that this is a capital sigma, and it means sum. This is used in math courses as well. So we use a sigma in front of that x to indicate that this formula takes the sum of all x values and then divides that sum by n. So for purposes of these questions, we will consider Lake Travis levels over any given time period to be a population. You could consider it to be a sample if you wanted to think of Lake Travis water levels over a 10-year period, for example, to be representative of Lake Travis water levels over all time since the dam was built. We're going to consider it to be a population just because there are probably other factors that affect the water levels over these years, and we don't necessarily think these are representative, but one could argue it either way, which is why we're explicitly stating it here so that we know what notation to use. The mean is 667.05 for our data set. We're going to write this using appropriate notation. Because we consider these to be a population, that notation is going to be mu. So I would write this as mu is equal to 667.05. Now we can also break up our time period into two time periods. So during the 80s and 90s, we have one water level, and the mean since the year 2000, we have another water level. We want to write this difference in means using appropriate notation and interpret it. Since we have a difference in means, we're going to have more than one mean, and we have to use subscripts. So I might say mu sub 80 for our 80s and 90s. And we'll say that one is 675.0. Mu sub 2000 is 660.5. Now I can decide what order to subtract in. Usually if I have the choice, I'm going to subtract in the order that gives me a positive number because that's a little bit easier to interpret. So I'll write this as mu sub 80 minus mu sub 2000. And that's going to be what I get by subtracting these two numbers. 675 minus 660.5 gets me 14.5. So this is writing the difference in means using correct notation. I have to know that they're called mu because they represent a population. I have to use subscripts to clearly differentiate between the two means, and then I can write the value. For interpreting it, we want to describe what that number means. This is a difference in means. It's a difference in mean lake levels for Lake Travis in particular. It's measured in feet, and I know that the difference is taken over these two time periods. So I want all of those little pieces of information to come across in my interpretation. Furthermore, I know that it was greater in 1980s and 90s, right? Since we took the difference in this order and it's a positive value, I know that the one I started with is the greater value. So when I interpret this, I'm going to describe it as how much higher the lake levels were on average in the 1980s and 90s than they were in the years post-2000. So I just took a stab at writing this sentence here, but let's call our attention to a few details. Lake Travis water levels is what we're talking about, so that's got to show up in my interpretation. On average, that reflects the fact that we are talking about means, right? So we need to have on average or the mean or something referring to what that actual letter represents somewhere in our interpretation. The number itself and its units, so 14.5 feet, and also an indication of which of these is the greater value. It was higher in the 80s and 90s than in the years since the year 2000. So I'm just underlining the things that we want to make sure aren't left out of our interpretation. So another example where we're talking about means and using correct notation. This is a sample of 351 diamonds, so we know that we're working with a sample and not a population. This is not the population of all diamonds. The mean is 64.4 millimeters for the depth, and so we're going to use X bar for this mean because this is a sample mean, and say that X bar is equal to 64.4. Now, similar to what we just did, we're going to break this sample into two pieces. We have a mean depth of our SI3 diamonds, right? Slightly included grade 3, we abbreviate that SI3. And that mean depth is 61.8 millimeters. The mean depth of internally flawless, which we abbreviate IF, diamonds is 64.6. So for this difference in means, we're again going to need some subscripts. X bar sub SI3 is equal to 61.8. And X bar sub IF is equal to 64.6. It looks like our internally flawless diamonds are on average a little bit deeper than our low-grade diamonds. So I'm going to choose to subtract X bar sub IF minus X bar sub SI3. But note that you could absolutely subtract in the other order. That would be fine. You would just get a negative result. And this is almost 3, so 2.8. We have a difference of 2.8, which means that in this sample of diamonds, our internally flawless diamonds are on average 2.8 millimeters deeper than our slightly included grade 3 diamonds. For brevity, I think it's okay to use the IF and SI3 abbreviations here because those are official abbreviations for diamond clarity. And you could also have said this as the depth of the IF diamonds are on average 2.8 millimeters greater than the depth of the SI3 diamonds, which might be more similar to how jewelers would actually talk about them. This deeper is a little bit awkward here. But this has all of those important elements again in this sample, so make it clear that we are not talking about all diamonds with this statement. Internally flawless, on average, again, referring to the fact that we are talking about a mean, 2.8 millimeters, we used some units with that, and indicating which one is greater than the other, deeper or greater depth or something like that. When talking about center of a distribution for a quantitative variable, Mean is one of the very commonly used ones, and median is the other. For median, we have to have a sorted list. It's very hard to find the median of a list that isn't in increasing or decreasing order. So we have those lake levels written here in increasing order, and each row has 10, so this is 37 total. This is 37 lake levels. So to find the median, we want to find the value such that half of the observations are smaller and the other half are larger. Half of 37 is 18 and a half, and if we think about what it would mean for 18 and a half of these to be smaller and 18 and a half of them to be larger, then we know that we're looking at the 19th value. So the 19th value is right here. What we really get is that 18 are smaller and 18 are greater. So we're aiming for the middle is what happens. If we have an odd number of values like we had here, then when we aim for the middle, we're going to get an actual number. So the median, which we often abbreviate with this lowercase m, is 673. We don't really get into the question of median of a sample versus median of a population, simply because we don't do any inference about the median in this course. But you certainly could use a capital M for median of a population if you wanted to. Any M is really okay. We don't really belabor the notation for median in this course. We just want to be able to find it. If we had an even number of values, say we had something like, let's just up here put a quick little list, 2, 3, 7, 8. Then when we aim for the middle, we end up right here in between two values. So if we have an even list, then we have to take those two center values and average them. You might be able to just eyeball the average because there's only two of them, but if you want a formula to use, you would add them together and divide by 2, which in this case gets you 5. But of course, just looking at 3 and 7, you can probably tell that 5 is the value that is equally spaced between them. All right, so this is the details of computing the median from a list, but sometimes we want to estimate the median from a graph. So what we're going to do is mark both of these on the histogram on page 1, both the mean and the median, to see what they look like on this graph. So here's our histogram. The median that we just found is 673, so that was our M. And the mean that we found previously, mu, was 667 plus another 0.05, something like that. Oops. Shouldn't have said point while I was writing that. 667. So our median is just a little bit to the right of 670 here. That's our M. And our mean is a bit to the left of 670 there. That's our mu. We can see in this distribution they're not the same. In some distributions they are. Sometimes the mean and the median are equal, and what really determines it is the direction of the skew. So what happens is that these values down here, for the median, we don't really care how small they are. All we care is that they are smaller than 667. They don't have any more impact on the median being way down here at 620 and 630 than they would if they were, say, over here somewhere, right? And so the median doesn't really get pulled to the left by those values, but the mean does. So the mean is pulled by the skew, relative to the median. If we know where the median is, we can just imagine that the mean got pulled a little bit more in the direction of the skew. How much more? It depends on how heavy the skew is. In this case, there was enough skew to have a noticeable difference, but we didn't have extreme outliers, so they're still fairly close together. Oh, whoops, actually I drew this way off. I drew this at 663, and in fact, let me take care of that. This mean is really over here. So I'll erase this previous mark, even though it's also going to erase some of the graph. So they're actually a little bit closer together than I made them look in my first drawing. Another thing that we can observe about locating the median here is that if we imagine drawing a vertical line at the median and looking at how much bar graph we have now on each side, we have a certain area over here, and we also have an area over here on the other side. The median is easiest to estimate from a histogram as being the point at which you have equal areas on both sides. It's not really easy to estimate those areas because they're generally pretty odd shapes, but we just keep tweaking it until we're convinced that those areas look approximately equal to each other. Then once we have established the median, we know the mean is going to go in the direction of skew if there is any skew in the graph. If there's no skew in the graph, then the mean lands exactly right on the median.